All right, strap yourselves in because today we're taking a deep dive into Einstein's theory of relativity.
Ooh, sounds fun.
You bet it is. And to help us make sense of it all, we've got a mountain of physics notes to sift through.
A mountain. That sounds like a challenge.
It is, but we're up for it. And you know what's really wild? Something as everyday as GPS simply wouldn't work without relativity.
You're right. It really highlights how fundamental this theory is to our modern world.
Absolutely, it's mind-blowing. So let's dig into these notes. We see the Lorentz transformation popping up quite a bit.
Ah, yes, a cornerstone of special relativity.
I've heard the name, but honestly, I'm a little fuzzy on the details. What does it actually mean?
Well, picture this. You and I are watching a rocket launch. I'm standing still. You're on a speeding train.
Okay, got it.
Now, before Einstein, physicists thought we'd both agree on precisely when and where that rocket takes off. Time was seen as absolute, unchanging.
Yeah, that seems intuitive, right?
Right, but Einstein's genius was recognizing that the speed of light is constant no matter how fast you're moving.
Interesting.
So for both of us to measure the same speed of light, even though we're moving relative to each other, our measurements of space and time, well, they have to be connected somehow.
Oh, I see.
And that's where the Lorentz transformation comes in. It's the mathematical magic that reconciles those measurements.
So wait a minute. If where and when that rocket launches looks different to each of us, just because we're moving at different speeds, does that mean there's no such thing as one true time?
That's the heart of it. It really throws a wrench into our everyday idea of time as this universal ticking clock.
Whoa, that's trippy. My now might be different from your now.
Precisely. In relativity, events like that rocket launch have different coordinates based on who's observing and how they're moving. It's all relative, you see.
Okay, my brain is already starting to bend. This is seriously challenging my perception of reality. But tell me, what are the real-world consequences of this relative view of space and time? Like, does it just stay theoretical, or does it affect things we can actually observe?
This is where things get really exciting. This relative view leads to some truly mind-boggling phenomena like time dilation and length contraction.
Right. I've heard these terms before, but they sound like something out of a sci-fi movie.
They do, don't they? But this is real physics. Let's take time dilation, for example. Imagine one twin chilling on Earth while their twin blasts off in a spaceship at near light speed.
Okay, I'm picturing it.
When the space-traveling twin returns, they've aged less than the Earthbound twin.
Wait, what? They literally experience less time. That sounds like something out of Interstellar.
It does. But it's not just a theoretical concept. We've actually verified this with atomic clocks flown on high-speed jets.
Seriously, so time really does slow down at high speeds.
This is wild. What about length contraction? That one sounds equally bizarre.
Length contraction means that objects appear shorter in the direction they're moving, at least from the viewpoint of someone standing still.
So if I'm watching a spaceship zip past at near light speed, it'll look squashed in the direction it's traveling, like someone sat on it. Yeah, it's like the fabric of space-time itself is being warped by the object's motion.
So let me try to get this straight. If I was on that spaceship, time would slow down for me relative to someone on Earth, and the distances I travel would actually seem shorter. It's like the universe is playing by a totally different set of rules.
You got it. Space and time aren't those rigid, absolute things we experience in our everyday lives. They're dynamic and interwoven in this four-dimensional fabric we call space-time.
This is a lot to take in, but amidst all this weirdness, does the theory at least keep things orderly? Like, does cause still always come before effect?
Absolutely. One of the fundamental principles of relativity is preserving causality. No matter how fast you're moving, you can't go back in time and mess with the past.
Okay, good. That's reassuring to know. So each with all the warping and bending, there are some limits. I'm also curious about this light cone idea I keep seeing in the notes. What's that all about?
Ah, the light cone. Think of it as a way to visualize those limits of causality in space-time. Picture yourself at the very tip of a cone. The events within the cone above you, that's your future. The stuff you can potentially influence. Events below, within the cone, that's your past, stuff that could influence you.
Makes sense so far.
But then, outside of that cone, there's a whole lot of elsewhere events you can neither affect nor be affected by. It's all because information can't travel faster than light.
So the speed of light is like a cosmic speed limit, creating a boundary in space-time. That's why it's called a light cone.
You nailed it. The cone maps out every possible path light could take from where you are in space-time. It sets the ultimate boundary for your sphere of influence, past and future. It's a pretty neat way to visualize the interconnectedness of space and time, isn't it?
It is. This is definitely stretching my understanding of how things work in the universe. Now, there's another concept in the notes that's piqued my curiosity. Four vectors. They sound a bit intimidating.
Oh yeah, they're key to understanding how relativity works.
Can you break them down for me? What are they all about?
Sure. Four vectors are basically a way to represent the intertwined nature of space and time in relativity mathematically.
Okay, so instead of thinking of space and time as separate things, three dimensions of space and one of time, we combine them into a single entity, a four-dimensional vector.
That's exactly it. And that has some pretty huge implications for how we understand things like momentum and energy, for example.
Interesting. So momentum isn't just about how fast something's moving anymore.
Nope. In relativity, it becomes a four-vector, incorporating both regular spatial momentum and energy. It's all connected.
Whoa, so momentum now also has an energy component. That's revolutionary.
It is, and that leads us to perhaps the most famous equation in physics, EMC-CA.
Ah, yes, the celebrity equation. We can't talk relativity without mentioning EFC-Ka, but what does it actually mean?
At its core, it captures this profound idea that mass and energy are essentially the same thing, just different sides of the same coin.
So even a tiny bit of mass packs a whole lot of energy, and that energy can be released under the right circumstances.
Exactly. That's why things like stars shine. Nuclear weapons have such devastating power, and we're working towards harnessing fusion energy.
It's amazing to think that this deceptively simple equation unlocks the secrets of the universe's energy. But how does this tie back to those four vectors we were talking about?
Well, with relativity, the ideas of conserving energy and conserving momentum, they're combined into one powerful concept, the conservation of four momentum.
So instead of two separate laws, it all comes down to one big conservation law.
Exactly. And this principle holds true no matter what reference frame you're in, even at those mind-bogglingly high relativistic speeds we've been talking about.
I'm starting to grasp how interconnected everything is in this theory. We've gone from the nature of time to four-dimensional vectors and the unity of energy and momentum. It's incredible.
It is pretty mind-blowing stuff.
Absolutely. But I think we need a moment to let all of this sink in before we move on. All right, we're back and ready to dive even deeper into the rabbit hole of relativity. Before we took a break, we were talking about how even energy and momentum get wrapped up in this four-dimensional view of the universe. Are there any good examples in these notes that really illustrate what that means in a practical sense?
Oh, there are some fascinating ones. Like, have you heard of the Compton effect? It's where a photon, something like an X-ray, actually loses some of its energy when it bumps into an electron. It's kind of like a microscopic game of billiards, but with subatomic particles.
Oh, yeah, right. I remember that from the notes. But hold on a second. If light is a wave, how can it have momentum like, say, a tiny ball? That seems a bit counterintuitive, doesn't it?
It does, right. That's one of the things that makes this so interesting. It was actually Einstein's work on something called the photoelectric effect that showed us that light can act like both a wave and a particle, a photon, at the same time. And these photons, well, they actually carry momentum. When they collide with an electron, they transfer some of their energy and momentum, and that causes the photon's energy to decrease.
So the Compton effect is kind of like proof that light can act like a particle, and that we really have to consider energy and momentum together, not as separate things. Wow, that's pretty amazing.
Exactly. It really underscores how energy and momentum are intertwined, just like space and time, and how this interconnectedness is key to understanding how particles interact, especially when you start dealing with those super high speeds we've been talking about.
Okay, yeah, I'm starting to see the bigger picture here, how it all connects. It's like a giant cosmic puzzle. Are there any other examples in these notes that illustrate this idea of for momentum conservation? Like, are there any other situations where it pops up?
Definitely. There's one that gets into the energy you need to actually create new particles. Picture two protons smashing into each other at like ridiculously high speeds. To create new particles from that collision, you need a certain amount of energy. You could say it's Einstein's famous EMC equation in action.
Right, because energy and mass can basically transform into each other. So you can't just magically make new particles appear without having enough energy to make up for their mass.
Precisely. But it's not just the energy from the proton's motion that matters. You also have to consider their rest energy. This is the energy that's equivalent to their mass, even when they're not moving. And because form momentum has to be conserved, all that energy, and the momentum too, from those initial protons, it has to show up in the stuff that comes out of the collision, the final products.
So it's like a giant cosmic balancing act where you can't get something for nothing, even when you're talking about super high energy particle collisions.
That's a great way to put it. This conservation law, it's super powerful. It lets physicists predict how much energy you need at a bare minimum for these kinds of particle creation events, and those predictions, they've been confirmed over and over again in experiments.
Wow, okay, I'm starting to see how important this four momentum concept is. It governs how energy and momentum work, even in these super strange and mind-bending particle interactions. But honestly, my brain still kind of struggles with the idea that time can slow down and length can actually contract. Is there any way to make those concepts feel a little more intuitive?
Yeah, it's definitely a challenge to wrap our heads around, especially because we're so used to thinking of time as this absolute steady thing that just marches on no matter what. But in relativity, time is woven into this fabric of space-time. And just like you can warp and stretch a piece of fabric, well, the same thing can happen to space-time.
You keep mentioning space-time warping, and it makes me think of like wormholes and stuff from Star Trek. Is that actually what's happening? Like, is this real or just a theoretical idea?
It might sound like something out of science fiction, but it's been experimentally verified. And one of the coolest pieces of evidence we have comes from atomic clocks. They're super precise timekeepers. And what scientists did is they put these atomic clocks on airplanes and flew them around at high speeds. And when they landed and compared those clocks to clocks that stayed on the ground, guess what?
What happened? They were different.
The clocks on the planes were a tiny bit behind the clocks that stayed on Earth. And the amount of time difference, it matched perfectly with what Einstein's theory predicted would happen.
So just because those clocks were moving faster, they actually ticked slower. That's insane. Time itself was affected by their motion.
That's exactly right. And it's not just clocks. We've seen the same kind of time dilation effects in how subatomic particles behave at those really high speeds. Time really does slow down.
Wow, that's seriously mind-blowing. So theoretically, if I could hitch a ride on a spaceship traveling at near light speed, I'd actually age slower than someone back on Earth.
You would. Although getting to those speeds is a bit beyond what we can do right now, technologically speaking. But the principle, the idea itself, it's totally sound.
I think I'll stick to regular Earth travel for now. But if time can be stretched and warped like that, what about space? Does that get affected too?
Oh, absolutely. Remember that length contraction we talked about? Just like time, distances can get wonky depending on how you're moving. Imagine you're cruising along in a spaceship at nearly the speed of light, heading toward a distant star. From your perspective, sitting in that spaceship, the distance to that star would look shorter than it would to someone back on Earth, watching you zoom away.
So, from my perspective on the spaceship, I'd be able to reach that star faster because the distance has shrunk.
You could think of it that way, yeah. And that's why length contraction is so interesting when you think about the possibilities for interstellar travel, at least for the people on board the spaceship.
That's fascinating. But it also brings up a pretty big question. If time and space are relative, if they depend on how someone's moving, does that mean there's no such thing as a universal now? Like a moment that everyone agrees on happening at the same time everywhere?
That's a huge question that has been keeping physicists and philosophers up at night for, well, a very long time. In the world of relativity, there's no concept of something happening absolutely simultaneously for everyone. Two events that look simultaneous to me might not look simultaneous to you if you're moving relative to me.
So what you're saying is what's happening now for me might not be now for someone else. Like our entire sense of now, of this shared moment, is kind of an illusion.
In a way, yeah. The idea of now becomes relative to, depends on your frame of reference, where you are and how you're moving. And that, well, it really challenges our everyday understanding of time and how we experience reality.
This is seriously mind-blowing stuff. We've gone from time slowing down and distances shrinking to questioning the very nature of now. It feels like we're getting into some pretty deep philosophical territory here. But tell me, are there any practical applications for these mind-bending concepts of time dilation and length contraction? Like, do they have any real-world uses beyond just being really cool to think about?
Oh, absolutely. Beyond GPS, which we talked about earlier, and which really needs to take relativity into account to function properly, another key place where these concepts come into play is in particle accelerators.
You mean those massive machines that smash atoms together? What does relativity have to do with them?
Well, those accelerators, they get particles zipping around at speeds super close to the speed of light. And when you're dealing with those kinds of speeds, relativistic effects, they become really important. For example, time dilation means that particles that normally decay super quickly, like in a fraction of a second, can actually survive for much longer, from our perspective at least.
Oh, so their internal clocks are basically ticking slower because they're moving so fast, so they get to live longer from our point of view. And does that give scientists more time to study them?
Exactly. And length contraction also plays a role in these machines. The magnets that are used to steer and focus those beams of particles, well, they need to be designed to take into account that the particles look shorter in the direction they're moving.
So, without considering relativity, those particle beams would basically fly off in all sorts of random directions. It sounds like Einstein's theories are crucial for pushing the limits of physics research.
Totally. Relativity isn't just some abstract theoretical thing. It's the foundation for many of our modern technologies, and it's essential for understanding how the universe works at its most fundamental level.
I'm definitely seeing relativity in a whole new light now. It's incredible to think that these seemingly abstract concepts have such real world impact. But I think we need to take another quick pause before we jump into the final stretch of our relativity deep dive. Next up, the grand finale, general relativity. All right, we're back for the final act of our relativity extravaganza. We've journeyed through the mind-bending world of special relativity, where time warps and lengths shrink. But now it's time to tackle the big kahuna, Einstein's true masterpiece, general relativity.
This is where things get really interesting. General relativity, it takes us beyond those simple scenarios with constant speeds and dives headfirst into the realm of gravity. It's a completely different way of thinking about how gravity works, especially on those massive cosmic scales.
Okay, I'm ready to have my mind blown wide open again. But before we get lost in the depths of general relativity, can you give us a quick refresher on where we left off with special relativity, just to make sure we're all on the same page?
Sure, no problem. So with special relativity, the big takeaway was that space and time, they're not these separate absolute things. Instead, they're woven together into this four-dimensional fabric that we call space-time. And we saw how objects that are moving really fast relative to each other experience those weird effects like time dilation and length contraction. It's all about perspective, you
Yeah,
know?
those were some seriously trippy concepts. But you mentioned earlier that special relativity didn't quite handle gravity, like it didn't fully explain it.
Exactly. Special relativity kind of worked in a simplified universe where gravity wasn't playing a major role. But general relativity, well, that's where Einstein really brought gravity into the equation, and it totally revolutionized our understanding of how it works.
Okay, I'm all ears. So, how does general relativity change how we think about gravity? Isn't it just this force that pulls things towards each other?
That's the classical way of looking at it, the way Newton saw it. But Einstein, he came along and proposed this totally radical idea.
Hmm.
Gravity isn't actually a force. Instead, it's a curvature, a warp in space-time itself.
Whoa, a curvature of space-time. That's a little hard to picture. Can you unpack that a bit?
Okay, imagine you've got a bowling ball sitting on a trampoline. You know how the bowling ball makes a dip in the trampoline's fabric?
Yeah, I can see that.
Now just imagine that the trampoline represents space-time. And those massive objects in the universe, things like stars and planets, well, they create similar dips or curvatures in space-time. It's like they're warping the fabric of the universe around them.
Oh, okay. So instead of thinking of the Earth orbiting the sun because there's this invisible force pulling them together, it's actually following the curve of space-time that's created by the sun's mass.
That's the gist of it. It's like the Earth is rolling along a cosmic highway, but that highway has been warped and bent by the sun's gravity, so it follows that curved path.
That's a really cool analogy. It makes gravity seem a lot less mysterious and a lot more like a consequence of the shape of space-time itself.
That's one of the beautiful things about general relativity. And you know what else it explains? It explains why objects with different masses, like a feather and a bowling ball, fall at the same rate in a vacuum.
Oh, right, because they're both just following that curvature of space-time created by the Earth's mass, so it doesn't matter how heavy they are.
Exactly. And that was actually demonstrated pretty dramatically by one of the Apollo 15 astronauts, David Scott. He dropped a feather and a hammer on the moon where there's no air resistance, and they hit the ground at the exact same time.
I remember seeing that footage. It was incredible. It's like those objects were just sliding down the slopes of space-time created by the moon's gravity. Okay, so general relativity gives us this whole new understanding of gravity, but are there any other crazy implications that come out of it?
Oh, tons. One of the most fascinating predictions of general relativity is something called gravitational lensing.
Gravitational lensing. That sounds intriguing. What is that?
So picture this. You have a supermassive object, like a cluster of galaxies, and its gravity is so strong that it actually bends the path of light that passes by it. It's like a giant cosmic magnifying glass, distorting and amplifying the light from objects that are behind it.
Whoa, so space-time is playing tricks on us, bending the light so we see things that we shouldn't be able to see because they're hidden behind that massive object.
Kind of. This bending of light, it lets us see those objects that would normally be obscured. And it's not just visually stunning, it's super valuable scientifically too.
In what way? How does that help scientists?
Well, by studying how the light is bent, scientists can figure out how matter is distributed in the universe, and they can even learn about the properties of those distant galaxies that we're seeing through the lens. It's a super powerful tool for cosmologists.
Okay, that's seriously cool. What other secrets does general relativity hold about the universe?
It predicts the existence of black holes.
Black holes, you mean those cosmic monsters that suck everything in?
Yeah. When a huge star dies and collapses in on itself, it can create a region of space-time where gravity is so incredibly intense that nothing, not even light, can escape its pull.
So it's like a bottomless pit in space-time, a place where the laws of physics just, I don't know, stop working.
It's not a bad way to think about it.
Yeah.
Black holes are some of the most extreme and mysterious objects out there, and they really push general relativity to its limits.
It's mind-blowing to think that something as fundamental as the curvature of space-time can lead to such bizarre and awe-inspiring phenomena. Does general relativity have any implications for the universe as a whole, like on a really, really big scale?
It absolutely does. In fact, general relativity predicts that the universe is expanding.
Wait, the universe is expanding? Hold on, what does that even mean? Like, what's actually happening?
It means that the space between galaxies is stretching, causing them to move farther apart. And it's not just that they're moving through space, it's that space itself is getting bigger. It's like the fabric of the universe is being pulled in all directions.
Wow, that's a huge concept to try to grasp. So those galaxies are getting farther apart, but not because they're flying away from each other, but because the space between them is literally stretching.
You got it. And you know what's even cooler? This expansion was actually observed for the first time back in the 1920s by an astronomer named Edwin Hubble. His observations provided the first real evidence for this mind-boggling idea of an expanding universe.
So general relativity predicted this whole expansion thing before we even knew it was happening. That's pretty impressive.
It is, and the expansion of the universe has had a profound impact on our understanding of how it all began and what its ultimate fate might be. It's what led to the Big Bang Theory, the idea that the universe started as this incredibly hot, dense state and has been expanding and cooling ever since.
All right, I'm officially mind blown. We've covered so much in this relativity deep dive. We started with special relativity, explored time dilation and length contraction, and then ventured into the realm of general relativity with its warped space-time, black holes, and expanding universe. It's incredible to think that one theory can explain so much about how the cosmos works.
It's a true testament to Einstein's genius and how he reshaped our entire view of the universe. And even today, his theories continue to guide our exploration of the cosmos and its mysteries.
I feel like I've gained a whole new perspective on reality, like I'm seeing the universe with fresh eyes.
That's the beauty of science. It challenges us to question what we think we know, expands our understanding of the world, and deepens our appreciation for all the incredible wonders out there in the cosmos.
I couldn't have said it better myself. And on that note, I think it's time to wrap up our deep dive into the world of relativity.
It's been an amazing journey.
Thanks for sticking with us as we explored these incredible and mind-bending ideas.
And to all our listeners, keep questioning, keep exploring, and never stop being curious about the universe and all its mysteries.
That's what it's all about.